we'll go on to our next and final talk before the break. I'd like to introduce André Pugin for our next presentation. And André, when you are ready, you can go ahead.
You're just on mute, André. And André, we're just seeing your desktop currently. We're not seeing your presentation material just yet.
While André gets set up, I'll just remind folks that if you're just joining us, we are available to take questions. All the presenters are here today on the line, and if you do have a question, you can post that into the Q&A box within Microsoft Teams, and we'll get to your questions live if time permits. But we have allotted some time during just before the break to take some more questions. Presenters can also do this by text replies. So yeah, how are we doing, André?
I'm opening my PowerPoint presentation again. Apparently my team crashed, so.
Oh, yes.
Yeah, I tried. It's my presentation is starting. Hopefully, yeah, it's in front of me. So I go for a share again.
All right.
Oh, my team's presentation is disappearing again.
Oh no.
You may have to run it from your side.
No problem, André. I can go ahead and share it from my side if that makes life easier. You should see it coming up now.
Yeah. Are you seeing it now? It's all good? Yeah. Okay. I'm presenting to you, good afternoon. I'm presenting to you geophysical methods for enhanced site investigation for Aquifer Thermal Energy Storage, called ATS projects. My co-authors are Barbara Dittiker, Heather Crow, and Hazen Russell, and Don Ford from Toronto Conservation Authority, and we are from the GSC Canada. And I want to thank also Steve Hollish and Rick Gerber for their help in that type of survey. And here it, sorry, next. So ATS requires shallow aquifers to manage sustainable heat energy. This requires mapping of aquifers in southern Ontario. Geophysics is a strong support for local and regional mapping of aquifers, as we have done a lot in collaboration with the Ontario Geological Survey and various surveys across Canada. So we have used high-resolution seismic reflection, H/V spectral ratio that was described by Barbara before, and borehole geophysics run by Heather Crow. And you can find the detail of that survey and all the processing steps in open file 9076. Next one. Next. Here is South Ontario. I took that from Charles Logan and Dave Sharp, who gave me those figures. So that's the surface DAM. Next. And then we pass to the bedrock surface DEM with various shapes and troughs. Then the sediment thickness, next. Sediment thickness shows complex sedimentation highlighted before by OGS with a lot of borehole data. And we have done lots of seismic survey too. And the next one. So the superficial geology is also related with all these surveys. Next. So next we have the Laurentian Trough and Toronto down at the Lake Ontario. And then next we see the Laurentian Trough that is filled with various morphologies, channels, and the Oak Ridges moraine that crosses it. And water flows to the south of the ORM. Water flows down to towards the Lake Ontario. Next. So we have those 2 points that show landfills expected to flow down if there is a leak. It's expected to flow down towards Toronto. And our survey next is here on the red dot. It's the York University campus. Next. So here is the famous Dave Sharp's sketch of the structure. So we are looking for groundwater aquifers, and we see here the Oak Ridges moraine channels and the moraine on top that are potential for aquifers. Next. Then we have Aquitard, New Market Till. Then next, we have the Upper Thorncliffe Formation, which revealed to be quite channelized. The deep channels have cut through the lower section there. It's also a major erosion surface. And next, we find Dawn Formation and York Till at the base that are also potential aquifers, as we will see on this presentation. Next. So here's an example of the complexity of the deposits. There is various channels in the lower, upper and lower sequence sedimentary. And you see the point lower York University, the dot point, where we should try to find those of one of those features, possibly. Next. So that's the section now represented with the orange are aquifers. Next. Next, so we have 3 lines, Tennis Canada. Then next, Jan McDonald line, which is longer and go through the campus, and the chimney stack that we will present at last. Next. So here is the method now with the seismic source and first plan with the P wave, the vertical shaking and the horizontal shaking next in shear wave. Next, you see the land streamer, which is 72 meters long for recording various direction of waves that will be analyzed. And then we see here the new reshaped mini vibe that also has a very good result for faster acquisition if we want to do some more regional acquisition. Next. So here is a comparison of shear wave to the left, raw records, and the compressive P wave to the right. And you see that shear wave has a much higher resolution, higher quality data here. Next. So we see here the small portion of a section where you have the shear wave on top with a very high resolution and the compressive P wave on the bottom. Next. So we see here that the very near surface is well mapped with the shear wave and not that well with the P wave. And next, you see higher resolution, as I was mentioning, and next, you see some deformation in the P wave. It's probably due to the presence of gas next into the sequence, and the shear wave is not dependent on the type of porosity. So that's a big plus also for shear wave. When we have both, we can also diagnose if the type of porosity we get. Next. So let's go to Tennis Canada profile where we have a borehole calibrated. Next. Next. So here is the Tennis Canada seismic line, short line, 80 meters or so, and 2 cored wells that are present nearby, just to the southwest. Next. Here is the borehole site with some cores that were disposed here, and dimicton, lots of dimicton in these cores. And we see Barbara taking measurements of HVSR methods. It takes about 20 to 30 minutes of measurements per station. Next. So here is the spectrum from HVSR. You have a low frequency, 1.53 Hertz. That's the deepest resonance. And then you have a shallow resonance at 16.2 Hertz. Next. So this is the seismic profile here. We see some complexity, but also various reflectivities, various amplitude. Next. You see here the velocity downhole profile that we can measure, and we can see a fairly good match with the high changes in velocity with higher amplitudes at the near surface and further deep. And next, we can see that it matches also with the vertical seismic profile. With a higher amplitude in the lower part and some amplitude in the less amplitude in the near surface. Next. So here is the lithology. The green are till dimicton, and yellow sand and orange gravel. Next. Here's the section that matches with the borehole. Next. So with the HVSR, we can see next the new market till, which is the high frequency resonance on top, and then next Thorncliffe formation, and next Scarborough maybe formation. We don't have confirmation, but it's a fine clay. But that doesn't give a response in the HVSR, and the big response is next, the York till with the gravel layer that was used, is used for the A-tests for Tennis Canada. Next. So here is the borehole downhole log. I won't go into detail, but that gives incredible useful information for all the lithologies. I want to just show the value of that sand in the Thorncliffe formation at high temperature, elevated temperature, which could have been potential for an A-test site, and then the lower gravel next from down formation or York till. That is being used now. Next. So next section, Jan McDonald. It goes from south to east and southeast again. Goes next. So here's the entire section. We see very continuous reflection, and the metro station is blocking the signal here, so it's kind of blurred. Next. So we interpreted different layers as bedrock, A, B, dawn beds, Yorktill, C, Scarborough Formation, and D, Thorncliffe Formation, and then on top, F, the Newmarket Till. Next. So the good surprise was the chimney stack reflection profile. Next. So we see to the left the shear wave depth reflection, and to the right P wave depth reflection. What we see on the lower profile interpreted, that there is a sort of channel structure that shows up in the seismic reflection, either in the S wave or the P wave. S wave was more better resolution to see that. Next. So here is the section interpreted, and the first maybe potential for a test, similar to what we see on the Tennis Canada, this high amplitude reflection, maybe a gravel lens there, and then you get the channel next that it can be also filled with some dimetons, some clay, because it could be a subglacial channel. We see similar channel in the Scarborough Bluffs, very same shape, very same structures. So it's a network of Thorncliffe gravel, Thorncliffe channel that are good potential. Next. So in conclusion, on the contrary to electric airborne geophysical electromagnetic techniques that cannot be applied in an urban environment, the method presented here, seismic reflection, HVSR, and borehole geophysics, are excellent tools for mapping aquifers in urban environments. And we are looking forward to do more work like that to demonstrate at a more regional level to see to find aquifer and map these aquifer reservoirs. In their management plan, cities and regional areas should conduct regional geophysical survey combined with targeted borehole to characterize and plan the use of regional aquifer in order to provide rules for neighborhoods for using shallow geothermal sources. That's a collaboration with many people, and they'll know. I thank you very deeply. Thank you.
Thank you, Andre, and thanks for sharing your work there. We are just coming up to break time, but we'll take a couple minutes here just to see if there's any questions coming in. Yeah, if you have any questions for any of the presenters in this session, now would be a good time to post them. And I'm not really seeing any come up right now, but we did get a question. I'm wondering, Andre, just going back to Barbara's presentation, I'm wondering if maybe you would, you might know this answer because you were co-author, and maybe we can help this person. So there was a question about, for Barbara, was she using a Tromino for the HVSR work? Would you happen to know?
Yes, definitely. Yes, that's Tromino.
Okay, great. Thanks, Andre. Thanks for covering that, and hopefully that helps
wasn't
answer the
difficult
question.
to answer.